This is Professor Pelton. This is part 1 of chapter 5, section 6. So we're going to talk about rational functions. So essentially a rational function is when you have a ratio, right, which is the first part of the word, right, ratio. So you have a function over a function essentially. One caveat with rational functions is if the denominator is 0, you're going to have a domain break because we know from basic arithmetic you can't divide by 0. So there's going to be some breaks in the graph. And those breaks will vary in type. So if we determine the domain of each of these functions, it's basically where the denominator cannot equal 0, right? That cannot equal 0. So if I add 3, right, x cannot equal 3, essentially, right? So my domain is everything except for 3, right? So negative infinity to 3, union 3 to infinity. Okay, you might have to factor the denominator, right? So this cannot equal 0, but I need to factor it, right? So that's x minus 3 and x plus 3, correct? Because you think about it, this is x squared plus 0, x minus 9. So the only way you get 0 is 3 and negative 3. So x minus 3 does not equal 0, and x plus 3 does not equal 0. So you get x equals not equal 3, and x does not equal negative 3, right? So my domain is negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. Okay, make sure it is in ascending order, like all domains in each of the chapters you've covered. Okay, so this cannot equal 0. However, if you try to solve x squared plus 9 is equal to 0, you're going to get x squared is equal to negative 9, or x is equal to plus or minus the square root of negative 9, right? Which is 3i, or plus or minus 3i, right? But that doesn't give you a real answer. So basically, this domain is everything, because there is no value that will make that denominator 0. No real value anyways. Okay, so this one's already factored out for us, which is nice. So that can equal 0, right? So my domain breaks are at x equals 0, x minus 2, or cannot equal 0. So x cannot equal 2. And then what is this? X plus 5. So x plus 5 cannot equal 0. So x cannot equal negative 5. All right, so going in ascending order. So my domain, negative infinity to negative 5, union negative 5 to 0, union 0 to 2. What am I doing? Yes, that's fine. And then union 2 to infinity. All right, I just had to check with myself here. Make sure I did them in ascending order, right? It has to be in ascending order. All right, pause the video. Try the student problem for yourself, or student problems. Okay, so that cannot equal 0. So domain is negative infinity to 5, union 5 to infinity. So this one we have to do some factoring, right? So you get x minus 5 and x plus 5, right? Because essentially it's a 0x term in the middle, correct? Because you have x squared plus 0x minus 25, sorry, minus 25. Minus 25. Okay. All right. Not equals, not equals. Okay. So essentially you get a domain of negative infinity to negative 5, union negative 5 to 5, union 5 to infinity. Okay, that's a very, very flat infinity. Okay, so this one cannot equal 0, but no matter what you plug in there, you can never get a 0, right? Because if I solve that, I get x squared equals negative 25, or x equals plus or minus the square root of negative 25, right? Which is plus or minus 5i, right? So there's no real answer that'll give you 0 down there. So basically there's no restriction. Okay, so we're going to talk about arrow notation now. So the arrow just means what you're approaching. So you can approach a number from the right side, or you can approach a number from the left side. That's what the positive and the negative means when it's in the exponent. Or the x value, you can just approach infinity or negative infinity. Okay, so there's 4 things you can possibly do. You can reach the infinities or approach them. Can't actually get there, obviously. Or you can approach a number from 2 different sides. Okay. So if you do that, what's happening essentially to the function value? So if I look at this particular graph right here for basic understanding, as x goes to out to positive infinity, the function is going down to 0. You never get there because, again, you're doing 1 over x squared, right? So if I plug in infinity into there, okay, it's essentially 1 divided by infinity. But anything divided by infinity is 0, right? If I go the other way, as x goes to negative infinity going out this way, the function is also going to 0. Because if I do negative infinity, it won't make any difference to the actual answer. Okay, although we don't need to calculate anything, I'm just looking at it graphically. Okay, so if I approach 0, so this is x equals 0 right here, correct? If I approach from the right-hand side, right, the function is going to positive infinity, correct? If I approach from the left-hand side, it's also going to positive infinity. Okay, so from the left-hand side, from the right-hand side, which is the positive negative side of the graph, and oriented to x, correct? It's both going up. And you can prove that to yourself by putting in very small values, right? So you can do 1 over 0.0001 squared, right? And you'll see as you keep making a smaller and smaller number, it's going to infinity, okay? So that's the basic idea of the arrow notation. What are you approaching, essentially? Okay. All right. So that gets into vertical asymptotes. So those domain restrictions we had before could be a vertical asymptote or a hole. Okay. So as you approach that particular value, it's going to go up forever or down forever as a function value when it tries to approach that x equals a. If it cancels top and bottom algebraically, then you have a hole. Okay. So let's see what that is essentially. All right, so either have a hole or a vertical asymptote here. You can verify with a graphing calculator. So if I in fact factor this, I'm going to get x over x minus 3 and x plus 3. So nothing algebraically cancels. So my vertical asymptotes are x equals 3 and x equals negative 3. Okay, and you can prove that to yourself with a calculator. So we'll do a ratio, and then x over x minus 3 and x plus 3. And you'll see at negative 3 and then positive 3, we have vertical lines you can't actually see. So we'll graph a relation, x equals 3, and graph relation x equals negative 3, and you'll see. So basically what we have here, make it dotted, right? We get a dotted line there, attributes, and we got a dotted line here, right? So you have an invisible line it can't cross. So it's either going to infinity or negative infinity, depending on which side you approach it from. Okay, let's look at the next one. All right, well, the next one, if I do, it works very similar, except I have x plus 3 over x plus 3, x minus 3. So those will actually cancel and leave me with 1 over x minus 3. Okay, so I have a vertical asymptote at x is equal to 3, right? Because x minus 3 cannot be 0, so x cannot be 3. So the vertical asymptote is 3. X equals 3. Graphically, that's the equation of the line, right? Just like we just put in the calculator. However, this other one canceled, okay, which means we have a hole at negative 3, right? Okay, well, if I plug that in, I get y equals 1 over negative 3 minus 3. So I get negative 1/6, right? Because again, I'm just using this equation here to figure out what that hole is. So if I modified this equation I just did in the calculator, and I change this to what I had, which I believe was what, plus 3? Okay, you notice it changes the graph. So these don't exist anymore. Oh, that one did. I'm sorry, that one still did. So only this one exists now, x equals 3. The other one didn't exist anymore. So we do have a hole over here, though, but you can't actually see it in the graph because it's microscopic. Okay, so the last one, well, the question is, does x squared plus 9 factor? No. And if I try to solve that, it's not going to give me a 0, right? Because I'm going to get x squared equals negative 9, x squared equals plus or minus root 9, which I'm sorry, the squared's already gone away, which is plus or minus 3i. So there's no real number we can plug in there to get a 0. And it doesn't actually factor because negative 3 and positive 3 don't give you negative 9. So the answer is none. There's no vertical asymptotes or holes for this particular problem. All right, pause the video, try student problems for yourself. Okay, so we're going to factor this problem. So I get x and then x minus 1 and then x plus 1. Okay, so the vertical asymptotes are x is equal to 1 and x is equal to negative 1. Because if I solve these, right, I'm going to get x is not equal to 1 and x is not equal to negative 1, right? So the holes, there's none because nothing canceled, right? I didn't take anything out. If you take something out, you're left with a hole, right? Kind of makes sense. So here I get x minus 1 over x minus 1, x plus 1 when I factor it, right? So I'm left with 1 over x plus 1. So now, since something was taken out, I have a hole. So vertical asymptotes, I have x is equal to negative 1 because x plus 1 is cannot equal to 0. So x cannot equal to negative 1. So the hole is at negative 1, right? Because I took this out. So if I solve that, the positive 1, excuse me. So y equals 1 over 1 plus 1, so I get 1/2, right? Because I'm just using the actual function that is left over. And then here, there's nothing you can plug in there that's real that would actually work, because x squared does not equal to negative 1, or x does not equal plus or minus the square root of negative 1, or essentially plus or minus I, right? So there's no real value you can plug into there. So there's none of each. There doesn't have to be. Okay. That is the end of part 1.